Okay, so we'll move on to something a little bit different here. Obviously, still using product rule and quotient rule. So let's take a look at this function. Y equals e to the x over the square root of x. All right, in part A, we are going to find y prime using the quotient rule. Turns out in part B, I'll just give you a heads up, we're going to find y prime using the product rule. So it turns out occasionally you have a choice. Now they will result in the same derivative, but it kind of depends on how you look at it. So okay, if we think y equals e to the x over the square root of x, and maybe at first we pay attention to that square root, we need to think of that as a power of x if we're going to use the quotient rule. So let's rewrite it this way. Y equals e to the x over x raised to the 1/2. Okay, now we can use quotient rule. Sometimes things take a little bit of rewriting before they're ready for a derivative, like something like this. Okay, well, we've got the low, we've got the high. So following quotient rule, to get y prime, here's the whole thing. But let's talk through each part. We've got y prime equals low, just copied, times d high, the derivative of e to the x. Well, we know that is itself, so we got low d high, minus the high, now that's the original high, times d low, derivative of low. Well, hey, now we got the power, so the 1/2 comes down in front. X raised, and we subtract 1, 1/2 minus 1 gives us negative 1/2. Low d high minus high d low, and it's all over the low squared, just like that. And there is your quotient rule. There's some simplifying we can do, but that's the calculus. Okay, so something I want to point out here. When you guys have your test, there are going to be questions that say something like simply take the derivative using the quotient rule. And in those questions, I'm also going to make really clear that simplifying is not necessary. So we've done the quotient rule. For test purposes, you won't have to simplify. So I could just circle my answer right there, and I'm set. Okay, which is, it's different. Normally, we always have to simplify everything, right? I'm now going to work through what it looks like to simplify this just for our edification. But on a test, if I say, take the derivative, and there's a quotient rule and you do it, then I'm also going to put in the instructions, don't simplify. So you would just stop right there. Of course, a lot of times we do need to simplify derivatives because maybe we want to plug a number into it, and we prefer the simplified version to plug a number in, maybe to find the slope of the tangent line. Maybe we have something else we need to do with the derivative after we have it. Maybe we need to solve something, or who knows, kind of as the course progresses. And in those cases, we definitely want to work with the simplified derivative. So let's just practice that now. It's a good idea. I'm going to repeat. Okay, ignore what I've got going on over here for the moment. Just pretend that's not there. So I'm going to remove my dots, obviously. And I'm going to put this 1/2 x to the negative 1/2 out in front of the e. Normally, we put the x first, right? The constant, I should say, first, then the power of x, then the e when we've got a term like that. Okay, so it's x to the 1/2 e to the x minus 1/2 x to the negative 1/2 e to the x, and of course, x to the 1/2 squared is just x to the first. So already that looks a little bit better. But now this is still not fully simplified. Why not? Because we've got a fraction inside of a larger fraction. Okay, 1/2 is inside of a numerator of a bigger fraction. So that's not simplified. Also, we have a negative exponent inside of a larger fraction. So a lot of times we're okay with negative exponents, But if they're inside of a fraction, that's a different story. So that's really the same idea, right? A negative fraction is like a negative exponent, excuse me, is like a fraction. So that's kind of the same rule happening twice there. Okay, so what's a good way to simplify this? And I know people there's more than one way to do it, and a lot of times people suggest things a couple different ways. I'm going to show you guys what I feel is the simplest, the most straightforward way to simplify a case like this. Okay, look at the parts that are the fractions, right? The 2, and in this case, if you thought of the fraction, it would be 1 over x to the half, right? So I got the 2 as the denominator of this fraction, and here, if I thought of it this way, x to the 1/2. If I multiply by 2 x to the 1/2, then those fractions within fractions are gone. All right, so that's what I'm going to do out over here. 2x to the 1/2. Why? Because I've got, if we think of the whole thing, I've got a 2 as my denominator here. I have an x to the 1/2 as my denominator there. So if I multiply by 2x to the 1/2, it's going to cancel these out. Now to do that, I need to multiply it to both terms in the numerator and the denominator as well. So that might be a lot. It's a lot of times in teaching it in a class setting, people are like, wait a second, can you explain that again? And I get it. This is like, that's that algebra that it's not technically new, but it catches us off guard because we're not used to working with this sort of thing in this way. Okay, so what's happening? If I multiply my numerator by 2x to the 1/2, so I'm going to start by multiplying it here. Well, I'll have the 2, right? But even check this out. X to the 1/2 times x to the 1/2, you would add exponents. That'd be x to the first. Okay, let me pull this down. We'll talk through it. So 2x to the 1/2 times x to the 1/2 e to the x would be 2x to the first e to the x. Pretty nice. Minus, when it multiplies here, it cancels both of these, and all we have is e to the x. And then when we multiply it to the denominator, well, this is x to the first. So when we multiply, we've got the 2, but then we can add 1 and 1/2 and get 2x to the 3/2. This is the simplified version. And so again, we might need that simplified version, let's say if we were going to plug a number in, or maybe we had something else that we were going to do with this. Okay. Let's move on. That was using the quotient rule for the derivative. Let's do the same function, and it's hard to fit all this on the screen. We're gonna, part B is now go back, find f prime again, but using the product rule. And think, how are we gonna do that? Okay, if we think of it in this form, I mean, we've been talking about it already. Think of moving this x up and make it a negative exponent. So think of the function now, slide this up. Think of the function now as y equals x to the negative 1/2 e to the x. So this is still the original function, but we have rewritten it again. Okay. Well, now I've got a product. First times second. So taking the derivative in this way, well, the first negative 1/2 x to the negative 3/2 when you subtract, times the second left alone, e to the x, plus the first part left alone, times the derivative of the second part. Well, that's the same in this case, e to the x. And if this was on a test, you could stop right there. Maybe you prefer to remove those dots because I don't, as your final answer. I don't know. Now, here's what's interesting. If we answer this way, we might be okay with that as the simplified version, depending on the situation. And maybe a good exercise, I won't do it here in the video, but go back. I'll just pull that last answer. Maybe go back and justify to yourself that these really are the same expression for the derivative or function for the derivative. We've got the denominator there, x to the 3/2, and you could kind of imagine that happening, that tucking under to give you 2x to the 3/2, and you'd have to find a common denominator, and it would work out. Okay, I won't do that here though, but if you want to look into that. Okay, moving on. What do we have next? Let's take a look at this function. Y equals 5x e to the x. What are we going to do with that? Part A. Hey, it's the normal line. Let's find the equation of the normal line at the point 0, 0. Okay. So we'll have to remember the normal line is perpendicular to the tangent line. So that'll come into play. First thing we need to find the equation of the normal line is the derivative. Okay, we need to know the slope of the tangent line before we find the slope of the normal line. How are we going to do that? All right, well, to find the derivative, this case, there's only one way to do it. It's a product rule. And so there's that product rule. Let's talk through it. Derivative of the first is just 5 times the second plus the first times the derivative of the second. Okay, so we see a lot of e to the x here in this section. Well, because we don't have a whole lot to go on. All we know is polynomials and e to the x at this point. Okay, so there's our derivative, and I'll go ahead and remove my dots. I always kind of get a kick out of that. I like my dots, All right. What do we do now? Okay, so the derivative tells us the slope of the tangent line. All right. Let's find the slope of the tangent line at our point. Now, when we are given the full ordered pair, all we need to do is plug in the x value. Plug in x equals 0 to y prime. We can ignore the y value for the time being. We don't need that yet. Okay, so 0 goes in, so you might call that y prime of 0. That would be 5 e to the 0 plus 5 times 0 e to the 0. Think, well, what does this work out to be? Well, the 0 multiplying there, of course, just wipes out this whole piece. And e to the 0, you might remember, is equal to 1. Anything to the 0 is 1. So we've got 5 times 1 plus 0 for this whole thing is 5. Okay. Now we just found the slope of the tangent. And I'll refer to it as m. Here, the slope of the tangent is m equals 5 right there. But we're not looking for the equation of the tangent line. We want the equation of the normal line. Hey, do you guys remember how the slopes of perpendicular lines are related to one another? If two lines are perpendicular, what does that mean for their slopes? You might remember the phrase, the negative reciprocal. So we will take the reciprocal and then apply a negative sign. The slope of the normal line, m equals -1/5. Okay, so we've got the slope of our normal line. We also know it passes through this point, 0, 0. They both pass through that point. And so here we're going to wrap things up for part A. The equation of our normal line, we can start with the point slope form. Y minus 0 equals negative 1/5 x minus 0. And we simplify, easily to y equals negative 1/5 x. Okay, I'm not going to do it for this section, a Desmos, but if we were in class, man, I would do it, and I encourage you guys, go into Desmos, graph that original, and then graph this line, and you can see, the normalness, the perpendicularness to the tangent. It's kind of cool. Okay, there is a part B to this question. Oh, let's practice finding a higher derivative. Y double prime. It's a good time for it. Okay, well-defined y double prime. Let's remind ourselves of y prime. This is actually another case where you would want to have your first derivative simplified. If you had to find a second derivative, well, then you want to simplify your first derivative as much as you can. Obviously, this case, there really was nothing to do. But certainly there are other cases, right? Okay, so we got to take the derivative of what we see here. Okay, let's think about it. Well, this first part is just a constant multiple 5 times e to the x. So that derivative is going to be pretty straightforward. But this second part, that's another product rule. So we've got a product rule with another element added on. So remember the rule for adding, we can do the derivative of this plus the derivative of this whole thing. Just happens to be this whole thing is another product rule. Okay, so here we go, and I'll just show you everything. Let me pull this up a little bit. Okay. So this first part, well, the constant multiple 5 carries down. The derivative of e to the x is still e to the x. Then we move to the product rule. Well, that's actually the original function again, which is kind of nice. So we got 5 times e to the x plus 5x times e to the x. And these two come from just that piece there. We might as well simplify it. There's not much to do. 5e to the x plus 5e to the x. We can combine. So 10e to the x plus 5x e to the x. There's our final answer for the second derivative. Okay, that will finish this video. We got our grand finale examples. Actually, I think we got 2 more examples coming. So, yeah. Tune in for those.